So here you can see delta PL refers to what is the change in intensity, and this represent the triangular brackets here represent averaging of what is inside it. So PL is the power which is incident on the photodiode. It represents the light in terms of the power in terms of the intensity of light. So whatever fluctuations in the uh, intensity of light, that is put in the form of a ratio, and this is RIN. So based on the above three noise parameters, which is IN square for photodiode noise, and then IT square for the preamplifier noise, and IRIN square, we come to the total CNR. So in the denominator, what you see is the sum of the three mean square noise currents. Okay, you can see these expressions. This expression, okay, and this expression. So what you have is actually the sum of these, fine, or IRIN square in the denominator. The denominator is the sum of IRIN square and IT square and IN square, and the numerator as the carrier power, which is this, fine. So we have the carrier power, and this denominator has the noise power, the sum of the three noise sources. So this is the behavior of relative intensity noise. So x-axis is the injection current. So as the injection current increases, the relative intensity noise, the noise ratio, actually not just the noise but the noise ratio, falls. Back reflection is a phenomena which occurs whenever there is a cut in the fiber, or there is a in the fiber, if you have, say, some change in refractive index, then at that point you can have scattering. So that scattering can give rise to back reflected signals. So such nonlinear phenomena can occur in optical fibers, and this can increase the relative intensity noise. So for the limiting conditions, if the received power is in the low regime, like something of the order of say a few microwatts or something around some 10 to 100 microwatts of optical power is incident on the receiver. In that case, the preamplifier circuit noise is the dominating. That means here in this expression, the preamplifier part corresponds to this last term. So this would be higher compared to the other two terms, compared to RIN and the photodetector noise. Okay, if the input optical power at the receiver is in the intermediate level, so something of the order of 100 to 500 microwatts, then we have quantum noise. So this quantum noise is something which is directly in the detector. So the quantum noise refers to the detector noise. This would be the major contributing factor in case of when the input optical power is in the intermediate region, that is something around 100 to 500 microwatts. So when the intensity is of the order of a few milliwatts or slightly below that, you can say from zero point 0.5 milliwatts or higher, then the relative intensity noise plays the major role. That's what is the meaning here. And this is there's an example of how you can calculate different or how you can calculate the CNR if the different parameters are given. So limiting conditions meaning what would be the maximum noise. So the maximum noise or the carrier to noise ratio that is given by this curve, and you can see when the received optical power is uh, when the received optical power is from 0 up to 8 around 8 dBm, then RIN is playing a major role. So between 8 to 12 dBm, the quantum noise of the detector noise is playing a major role, and between 12 to 6 dBm, it is the preamplifier which is playing the limiting role. So there are multi-channel fiber transmissions. Multi-channel fiber transmissions refer to multi-channel fiber transmissions refers to using many subcarriers. Uh, so the subcarriers all can have different frequencies, and these frequencies, each frequency can be said to be a channel. So these are multiple channels which can be transmitted over a single fiber. Not just a single fiber, but a single wavelength. So if you multiplex multiple wavelengths, then similar subcarriers can be transmitted over multiple wavelengths, and the data carrying capacity or the information carrying capacity can be much more. So there are different methods by which you can have this multi-channel transmission. So FDM, VSBAM, FM, SEM, these are all I think standard multiplexing techniques, or which I think you have already gone through in your analog modulation classes. So this is about multi-channel fiber transmissions. After this, there is multi-channel amplitude modulation, and this is used in cable television networks. So in cable television networks do use optical fibers, or it's not necessary that cable television networks must use fiber networks. These days, of course, the satellite transmissions are much more popular, but before that, the cable networks were using optical fiber as a channel, where whenever the distance of transmission was very high. So uh, this this is the basic structure of how multiple channels were propagated over the optical channel. So this is about the modulation index for different channels and the combined modulation index. So these multi-channel amplitude modulation, uh, this is more of a legacy technology. These days, you can find most of the optical fiber technology is the optical fibers carry digital data. So the analog transmission is very rare, but this is legacy and uh, the initial starting of some of the applications. So frequency modulation using by using frequency modulation, multiple channels can be multiplexed onto a single optical fiber. Then the signal to noise ratio is given by this expression. And if you're using subcarrier multiplexing, well, this subcarrier multiplexing is an important uh, technology which is presently being worked for visible light communication. I have discussed about, I think, very briefly about visible light communication in during your classes also. So this subcarrier multiplexing is being used in visible light communications to enhance the data rates. So people are working on subcarrier multiplexing as a part of visible light communication now. So it's possible that this subcarrier multiplexing. So uh, uh, are you familiar with this term LNA, which is given here? Anyone? Does anyone know what is the full form of LNA? नहीं. Am I audible?
Yes, sir.
Okay. LNA refers to a low noise amplifier. So a wideband LNA refers to You have uh, this amplifier can work over a wide frequency range. Fine. So when you have multiple carriers, all these subcarriers use radio frequency or microwave frequencies. So these, if you want to detect all these frequencies, then you need wideband receivers. So for that, wideband uh, avalanche photodiodes need to be used. If the links are long distance of the order of some 20 kilometers or so, or even more. If the distance is of the order of 20 kilometers or more, then the wideband avalanche photodiodes are commonly used. If the distance is less, then a pin photodiode can be used. So after the photodiode, for amplifying the received signal, a wideband low noise amplifier or a pin FET. I think you're familiar with the field effect transistor. So a pin FET can also be used instead of a wideband LNA. The characteristics would be similar. So you get the proper amplification of the microwave signals. So this is about analog transmission. I think I have not shared these slides with you. I'll be doing that after the class today. Uh, okay, so going ahead, this is about digital transmission, which is what is being presently used throughout the world. So we have this is the basic part or basic part of a optical communication system. This is a single path. You can have multiple paths which would be combining together to form an optical network. So this is a point-to-point link wherein an information source is put onto the information source is usually in the form of some data. It can be any of voice, video, or data, and that is modulated onto light, which is done by a Mach Zehnder modulator, which you have already gone through in your labs. So the optical transmitter uh, converts this electrical source into optical form, and it transmits it onto the optical fiber. So the optical fiber trans, uh, transmits this uh, over the necessary distance, and the receiver converts the optical signal back into the electrical form, so which can be used by the user. So this is what is currently being used, and the system parameters that one usually needs to check are: what is the transmission distance? Is it possible to have a higher transmission distance? And what is the data rate or the channel bandwidth? And what is the bit error rate? So these are three basic parameters, apart from, of course, what is the power being launched and what is the power being received. That, of course, is dependent on what is the transmission distance. So in this point-to-point links, if you are a designer, then these are things that you need to take a look at. Should you use a multi-mode fiber or a single mode fiber? Uh, so when would you like to use a multi-mode fiber, and when would you like to use a single mode fiber? One basic thing is uh, distance. So if your distance is of the order of say some hundreds of meters, less than a kilometer, then a multimode fiber can work very well for you. The advantage of multimode fiber is low cost. So whenever the distance is less, you can always go for a multimode fiber. If the distance goes above 1 kilometer, then uh, we're already familiar with what is dispersion. So multimode fibers would give rise to higher dispersion, and accordingly you'll have to use single mode fibers to eliminate most of the multimode dispersion. So you're already familiar with the difference in core size, the core refractive index profile. Should you use a graded index fiber or should you use a step index fiber? And what would be the bandwidth, and what are the dispersion effects? How much attenuation would be uh, there along the optical fiber, and what would be the numerical aperture or the mode field diameter. So numerical aperture is a parameter which you usually need to check when you are launching light onto a fiber, and the mode field diameter is a parameter which you need to check when the light is coming out of the fiber onto a photodetector. So these are things which a designer should consider about what should be the preferred parameter for a particular point to point link. What should be the source? So what should be the uh, wavelength? What should be the line width? What should be the power? What should be the effective radiating area? The effective radiating area, of course, if the source used is LED, the radiating area is higher, and uh, it is easier to couple onto multimode fibers. And if you're using a laser, then the effective radiating area is much smaller. Of course, coupling even laser output is easier with a multimode fiber, but the advantage offered with laser diodes with single mode fibers is much more. So even with a small radiating area, even though it is difficult, people have found ways of coupling the laser output onto single mode fibers. And the emission pattern is important in what would be the mode which is propagating along the fiber. If the emission pattern is Gaussian in nature, which is normally the case, then you have a single mode propagating along the fiber path. And if the number of emitting modes is more, then you can have uh, intermodal between modes. You can have some power transfer or coupling of power from one mode to another. So that may be a deterring factor. So, in order to avoid this, a laser diode is chosen which is emitting only a single mode. Going ahead, what should be the photodiode to be used? Should we use a pin or an avalanche photodiode? So, depending on distance, if the received power is quite high, then you can use a pin. If the received power is low, then you can use a avalanche photodiode. So among these photodetectors, you need to check what should be the responsivity, what should be the operating wavelength, how fast should the mm, photodetector respond to the input light, and sensitivity refers to how low a level of optical light can the photodetector detect. So there are usually two budgeting schemes which are followed, and these budgeting schemes are the analysis, which is uh, necessary to show that this particular point-to-point link will work. So for that you need to do a link power budget and a system rise time budget. So the system considerations which you have to consider in a link power budget uh, is what should be the wavelength and how much is the uh, power at that wavelength. So, and accordingly, if this is the power being transmitted, what are the major transmission characteristics which are hampering or limiting this optical power from reaching the receiver? So, when a photodetector is chosen, then you must identify what is the minimum optical power that it can detect, so that you have a reasonable bit error rate or acceptable bit error rate uh, as per standard fiber optic communications. A bit error rate below 10 to the power minus 8 is considered to be acceptable. So, dispersion is a phenomena which is existing, and people try to minimize this as much as possible. So, data rate is higher the data rate, better is the transmission system, and of course, The transmission distance depends on requirement and cost. Lower the cost, better is the link. So going ahead, we have many choices which can be made, and for budgeting of power, connector and splice losses, and other environmental induced losses, all of these should be considered. Even what can happen because of temperature variations, and because of radiation effects, dust and moisture on the connectors, all these should be put into consideration. So, uh, well, uh, here this P in should be actually just below P out. So, this is the expression for loss in an optical fiber. So, P out refers to what is yeah. So P out is the power emanating out of the loss element. So the loss element here refers to the entire fiber, or it can be even a single component along the fiber. Like if you have a splice, it is a loss element. So what is the output power after the splice, and what is the input power after the splice? Okay, so if you look closely, P out will always be less than P in, right? So in and the logarithm of so the value of P out by P in is always less than 1. So when this value is less than 1, it is 0 point something. So when it is 0 point something, logarithm of 0 point something would be always negative. So the loss here is always negative. Okay. So uh, if you are doing a link power budgeting, then this is the kind of expression that you need to check. So PT here refers to the total optical power loss. So this is the difference between the power which is transmitted from the source and the power which is received at the detector, that is PS minus PR. And this total power loss would be depending on what is the connector loss. So LC is the connector loss. Okay, this here is LC. So LC is the connector loss. So it considers that there are two connectors in the link. One connector would be at the transmitter end and another connector at the receiving end. This is the minimum number. Of course, if it is an entire very large network, then it can be many number of connectors in between also. So apart from that, there is the fiber attenuation given by alpha f, and L here, capital L here refers to what is the length of the optical fiber. So this is a unit. This has a unit of dB per kilometer, and this has a unit of kilometers. So the overall unit for this is some dB. Okay, and we are already familiar. At 1550 nanometers, we have lowest loss of about 0.2 dB per kilometer. So beyond this, there is a system margin which is kept so that even if some other effects, as mentioned here, you can have some environmental induced losses. which arise from temperature variations or radiation effects or dust and moisture on the connectors. So these are considered under the system margin, and this is normally taken as 6 dB. So, so this is an example of how link power budgeting can be used. If we have a data rate of 20 Mbps and a bit rate of 10 to the power minus 9 for the receiver, if we are using a pin photodiode which is operating at 850 nanometers, the required receiver input signal is minus 42 dBm. Okay. So for these parameters of 20 Mbps, 10 to the power minus 9 and 850 nanometers, you can have for the silicon pin photodiode, it is something around minus 42, somewhere over here. Okay, corresponding to data rate of 20 Mbps. Clear? Anyone having any queries so far? Any queries so far? सारा समझ गए? मैं जो समझा रहा हूँ वो सुनाई दे रहा है या नहीं दे रहा है? Should I be louder or is it okay? So command line means simply you just open the command, give the command. So like in this one, in the line console, mail is the name of the command, give the command. Okay. Or these are the some examples. These are the lines. The user agent. Okay. These are having both these things. User agent they are having the. Should I continue? They are having the MPA. So these applications, mail or some other applications that we find. So these are some of the applications and you can retrieve the send detail if your application has also application. So most of the learning system and so. This is another example of how this link power budgeting can be used. This shows an gallium aluminum arsenide LED is used, which can couple 50 microwatts of power onto a 50 micrometer core diameter. So 29 dB is the allowable power loss and 1 dB is the connector loss. So LC is the connector loss of 1 dB. So it considers the two connectors, one at the transmitter end and another at the receiver end. And there is a how do you find the possible transmission distance? So if the allowable when the allowable power loss is 29 dB, PS minus PR is 29 dB, and this should include the margin. What margin? System margin. So alpha F into L must be or should be less than 29 minus 6 minus 3. So 20 dB. And if alpha F is 3.5 dB per kilometer, so you can have a transmission distance of about 6 kilometers. So this alpha F into L, this product should be less than 20. So if alpha F is zero point 0.2 dB per kilometer, then you can have a transmission distance of how much? Nobody seems to be listening.
10.5 kilometer.
कितना 10.5?
If alpha is 2 dB per kilometer.
Okay, if alpha is 2 dB per kilometer, yes, it is 10 kilometers. Fine. So, uh, uh, this is the graphical representation about the top line indicates how much power was fed from the source, and the most lowest line indicates what how much power can be sensed by the receiver. So in between, all other losses are indicated. So uh, now can you, for this particular example, can you identify what all things are given? Plus 3 dBm is the power from the transmitter into the fiber connector, and so this is PS, and APD has a receiver sensitivity of minus 32 dBm. So this is PR. So 3 minus of minus 32. This is the total power loss which is allowable. That comes to a total of 35 dBm. Okay. So at the data rate is given as 2.5 Gbps. The distance is given as 60 kilometers. Attenuation of zero point 0.3 dB per kilometer, and short optical jumper cable at each end. Uh, yeah, and if the jumper cable, there are two jumper cables, and each jumper cable introduces a loss of 3 dB, and there is a 1 dB connector loss at each fiber joint. Can you identify what would be how much margin do you have? In this, everything is given except for the system margin. Identify what is the system margin in this particular example. अभी करके बताओगे या कब बताओगे?
So now only. Nine dB.
Hmm?
9 dB.
9 dB is the system margin. 35 में से 60 into 0.3, so 18 is directly gone, right? Out of 35, So you're left with 17, and 6 dB is for the jumper cables. So you have 11, sorry, 17 minus 6 is 11, and 2 dB for the connectors. That's what you're considering, right?
Yes,
But
sir.
here, what he
So,
has
but
said,
PT is given in form of dBm and others are in form of only dB.
this we have already discussed, right? When we are discussing power, in the power is always the unit of power is always dBm, and when we consider loss, the unit is always dB. ये हम पहले भी डिस्कस कर चुके हैं, आई थिंक इवन लैब में भी ये डिस्कस हुआ है, आई थिंक.
Okay, sir.
दिस 1 dB कनेक्टर लॉस यहाँ पे सिर्फ दो कनेक्टर नहीं है. व्हेन यू आर यूजिंग जंपर केबल, at each jumper cable you have two additional connectors. Okay, so this is something which is something like a hidden component. So you do not have just two connectors, you have six connectors. यहाँ पे ये दिया हुआ है ना, सोनेट इक्विपमेंट रैक. सो दिस इज समथिंग इन बिटवीन द लिंक. ठीक है.
Yes, sir. Yes, sir.
सो ये सिस्टम मार्जिन नाउ इज कितना हो गया? 11
Five.
minus 5 dB.
Five.
Okay. So it's advisable to have a system margin of 6 or higher, but 5 is slightly less, so you should be uh, uh, better off if you can increase the uh, power of the laser diode by 1 dBm. Fine.
Sir, how we get number of connectors?
The- for every see, uh, what is mentioned here is a jumper cable, right? You're familiar with patch cords, right?
Yes, sir.
I have also shown this in the lab. In the lab also we have patch cords. So a jumper cable is nothing but a patch cord. So these patch cords have connectors at both ends. Okay? So each jumper cable will have two connectors. So there are four connectors in the jumper cable itself, and beyond that you have connectors at the source and the receiver. So you have a
Okay, sir.
total of six connectors. Fine.
Yes, sir.
But of course, here it's telling that assume that each jumper cable introduces a loss of 3 dB. So if you're if you can also say that you're assuming this loss of 3 dB to include the losses because of the connectors. In such a case, there'll only be two connectors. Clear? समझ में आया या नहीं?
Sir, can you please repeat it?
Now, this 3 dB may also include the loss of the connector uh, which is present in the jumper cable. ठीक है? So if this 3 dB includes that loss, then you should be considering only two connectors. Is that clear?
Okay, sir.
So this particular line is not exactly explaining what uh, what it includes. This 3 dB, does it include the connector losses or not? Fine. So if this includes the connector losses of the jumper cable, then you only have two connectors. Otherwise, you'll have six connectors. Okay. So I think we'll stop here for today. Uh, you can log out, and I think you have another class.